Cool, thank you, Peter. So I guess everyone can see my screen.
Actually, I can't. Maybe it's just my setup.
Oh,
Can
I
everybody
can
else
see
see?
it. I can see it.
Okay, then it's just my wretched Chrome. Okay, I'll sort it out.
okay. Okay, so I guess I don't need to re-share my screen. Okay, cool. Yeah, hello everyone to Paper Club. Today we're going to discuss about this paper that is called Llama Duo. So they claim it as an LLMOps pipeline for seamless migration from service LLMs to small-scale local LLMs. So where did I find this paper? Actually, I found this paper from one of the newsletters I'm subscribing to. And I thought like when I read the title, I thought, oh, it's LLM ops. So it's sort of like call my engineer mind. It's like, okay, I think this is something I can present. I'm uh I like to see like how uh practical we can implement this paper. So yeah, uh I like that because it has this engineering aspect. And then when I read the paper, I saw that it's quite practical. And yeah, and also this is a paper from Hong Kong University, and they have this collaboration with Hugging Face. So we can see here as well that they have this implementation and also the model checkpoints in Hugging Face. So I think it's like a quite good and very practical if we want to use their work. Okay, so what's the problem that this paper is addressing? Um, with this all of this LLMs hype that okay, normally when we want to use LLMs, we call, for example, Claude from Anthropic, or we call Gemini from Google, and it means that those models, those LLMs, are deployed in this like external parties infrastructure. They call it the service LLMs because basically we call their service, and it means that we really depend on them. It means that, let's say, the service is down, then our whole operation will be down too. And also we can have privacy issues because it means that we share our data with them. And yeah, like it's also it can also be very costly, especially with uh like high number of tokens. So the idea of this paper is that okay, we want to have the ability to migrate to a smaller LLMs that we can deploy and manage locally. Um, so it means that we no longer depend on them when, like, let's say the service is down, because we manage our own LLMs and they are like smaller LLMs. And I find it very important because then, as the application of LLMs like become more widespread, then we can see that, we can definitely not rely on this particular service provider. And if we want to use it in like longer time, we will see later in the paper that it has like much more economic benefit if we deploy it ourselves, because definitely we don't need to like spend a lot of money calling the service. Okay. What's the next thing? From what I can tell here, we don't have like similar solutions at the moment. I guess also because this paper approaches this problem from an engineer point of view, while we want to have this like a continuous LM of pipeline instead of just like coming with a smaller model, and then okay, we have this smaller model, and we don't know how we can implement it in our like day-to-day work. So yeah, I think this is also another unique point of this paper, that yeah, like it's very practical, and I don't see any like sort of like existing solutions from the paper that solve similar problem from this engineering perspective. Okay, so let's deep dive into this paper then. Oh yeah, just to before we go further, they have this implementation here. I will share this tab. They have this GitHub. What they claim here in this GitHub is that this is the template of the pipeline in the paper. So it's not meant to be used as it is, because you need to make it fit to your use case. For example, how you want to evaluate, what sort of data you want to use. So it's just a example of the template, but then you need to like use it for your use case. But I think it's very comprehensive. Yeah, well, definitely I didn't have time to try it myself, but I did a quick look at the examples they have here, and I find it very comprehensive. And they also have I'll share this tab, the checkpoints of the experiments they did in this Hugging Face repo. So yeah, if you're curious, we want to compare the results, you can get the. I think they also have the data set. Yeah, they have the data sets as well as the model checkpoints. Okay, so let's go to this paper further. So okay, so what actually in general the solution that this paper is proposing? They remember the problem is that with the service LLMs, we need to have like multiple calls to the service LLMs, and this can be pricey, and then we have to depend on the service itself, and it might have privacy issues, etc. So the idea is that okay, we want to have these smaller LLMs that we want to deploy locally, but then how? Because it's not easy, right, to come up with a smaller model, but we don't want to sacrifice the performance. So the idea is that, okay, we will have a pipeline. I think I will just go through this quickly because this picture really explains what's happening. So, okay, we will have a pipeline that we will fine tune a smaller LLM model, and then we check the performance. If the performance is good enough, that's good, then we can simply deploy this smaller fine-tuned LLM in our local environment. But if not, we want to increase the amount of the data set that we want to fine-tune on. And how we can get more data? We will utilize the service LLMs to generate synthetic data set. So this is an iterative process until the fine-tuned smaller LLMs can have like similar or maybe even better performance compared to the service LLMs. And then after that, we can deploy locally. So that's a very high-level idea on the solution of it. We will fine-tune smaller LLMs with scientific data generated by the service LLMs until we receive the desirable performance, and then use this small LLM moving forward, forget about the service LLMs. Okay, so that's roughly the high-level solution. And in this paper, they experimented with various tasks like summarization, classification, coding, closed question and answering. They also try all of these popular service LLMs like GPT-4o, Claude 3 Sonnet, Gemini 1.5 Flash, and the smaller local LLMs, Gemma, I don't know how to say this, Gemma 2B and 7D Mistral and Llama 3 8P. So they also want to showcase that with this method, we can achieve on-par performance with various kind of tasks. So we should not be limited by the kind of tasks we need to do. And they also want to show that how this method also works with different service LLMs, which I find is interesting. So, okay, just to summarize again, the key contributions of this paper. First, they introduced this LLMOps pipeline called Lamajo, which implement this concept to migrate from service LLMs to smaller and locally manageable smaller LLMs. They also um, like I would say like explain this idea of using synthetic data generated by service LLMs that will help fine-tuning the small LLMs to achieve on-par performance with service LLMs. They also show that this method can be implemented in various tasks, also various service LLMs, as the synthetic data generator as well as the evaluator. And they also mention later in the paper like how much money we can save by using this method. So what I think also interesting in this paper is that it's not that I would say like there are a lot of like small bits, small takeaways in this. So we can like follow how they generate synthetic data. We can follow how they evaluate the model. So not necessarily, let's say, we want to implement this paper. It's not necessary that we need to implement the whole system, but we can like get inspiration on how they implement like different stages in the pipeline. So that's what I think also very applicable in ASO. Yeah. Related work to this paper. As I mentioned, it's not this related work. It's not really solving the same problems. It's like solving a subset of the problems. For example, like with LLMs, with pre-trained LLMs that were trained on like a general data. Sometimes it doesn't work well with instruction tasks because they are not optimized to following human instructions. So that's why the idea with this pipeline is that we want to fine-tune the LLM on a particular task so that it can achieve the really good performance, because without specific tasks, then it's hard. I think it's like a very general common knowledge with LLMs and any other actually generative training. And the second point is, like the problem of amount of data, which is normally our bottleneck in, I would say, in general machine learning. And they showcase that, okay, it has been proven that, with more data, then there is more chance to get better model performance. And that's why the idea is that, okay, let's utilize this the big service LLMs to give us synthetic data. So they sort of like combine these different ideas in the pipeline. Yeah, I heard.
Yeah. So one question: does it mean that the big LLM is so good that you essentially don't need to fine tune it on your particular task anymore, and just ask it for the data, or
You mean that the service LLM is so good so that it can
yeah,
directly generate the data instead of
I mean, why is it synthetic, or why do we think that synthetic data is good enough that it can fine tune a smaller model?
yeah.
But
So what I've read here is like it's users, it's like it's human in the loop process that the human manually curate the data from that service LLMs, which I highlight here. So it's not like we directly use everything that is service LLM generated, but the human needs to like pick the good quality examples. So I think that's like like the laborious bit of it.
and in practice, how large would these sort of synthetic data sets be? For the fine tuning, would it be hundreds, thousands, tens of thousands?
Yeah, they mention it here. Let me find. They put it in the experiments. They put it here, like down in the experiments. We can talk about it later, but they put. Yeah, this is the volume.
Okay,
So what? Yeah, like they reach the saturation starting from like 64K.
okay. Yeah.
Yeah. Okay. So let's go back to this.
Yeah.
Yeah. Cool. So yeah, they started with this what they call coverage data set. It's like the curated data set that humans need to do by picking the most satisfying prompt and the response pairs from the service LLMs. They call it this data set D, and it's pretty straightforward that okay, we will divide this data set into train and test set. So yeah, now we have what they call like the seed data set for the train, and we will use the test set to evaluate. And then for the fine tuning itself, so okay, first with this coverage data set I just mentioned, we train on that, we fine tune on that train subset, and then we do this batch inference, meaning that okay, we have this fine tune model. Now we want to use this model to generate the response on the test set. And then the generated response will be evaluated against the ground truth response, which is the fifth stage here. And then we check, okay, if the matrix is above the threshold, then yes, we go to the seventh stage, which is to deploy. If not, if it's lower than the threshold, we will use the synthetic data from the service LLMs with this blue line here to continue the fine tuning until we achieve the threshold. So in general here, they summarize it with this equation, which basically that the metrics, the performance of the final small LLMs is basically based on the performance with this the initial data set and the synthetic data set for all of the iteration. So this is it called superscript here, meaning that this is the batch, not the batch, like the iteration of the synthetic data set over time until we achieve the desired performance. And for the batch inference, before we get to evaluation, so in order to prevent like bias and also to get like consistency, we generates not only a single response, so we generate k responses. So given this a test set that okay, sorry, this is not clear. So after we have this fine-tuned model, now we want to run the inference using the model that will be later compared with the ground truth. And how we do the inference, remember we have the test set in the beginning. We sample like a prompt from that test set, and then we ask LLM to generate a response based on this prompt, and we do it k times. So we will see the variation of LLM response k times, only one response. Okay, now we have these five responses for each prompt that we sample from the test set. Then the next step is that we want to evaluate these results. We use also LLM to evaluate this response. They call it service LLMs as a judge. And for each response, they run this evaluation m times. And this is part make sure that we have trustworthy and we reduce the bias of the evaluation. So again, we have 5 responses for each prompt, and then for each response, we run the evaluation m times. So then we can see here with all of this process, when we calculate the metrics of this LLM, we will have like the number of prompts times the number of generated responses, which is k, and the number of evaluation, which is m. So we multiply those. And what are the metrics they use here? They use first is the similarity between the generated response and the ground truth, and also the precision. So should I mention here? Yeah, they also calculate the mean, and I think also median. I saw it somewhere. Yeah, maybe not here. So yeah, they calculate the mean of the similarity between each ground truth response and the generated response, and the precision between the input prompt and the generated response. And because we have k responses and m evaluation, then we just multiply them. And they also introduce here a matrix they call coverage percentage. Basically, they pick only the test examples that has the metric, let's say the similarity above a particular threshold, and run the mean. So it's like a threshold when we think that it is good enough. Okay, we only take that proportion that are good enough, that have met or exceeded the benchmark, and then we compute the mean over that. Okay. Yeah. Okay. Then we run this evaluation, and then let's say apparently that the performance is not good enough. Okay, now that's the time when we want to generate synthetic data. Yeah, to generate the synthetic data, we use the LLM. So the service LLMs have a lot of roles here. First, it it generates the synthetic data. Second, it is used as the evaluator, and third, it's also used as the benchmark of the performance. And we can use different combinations of service LLMs when doing this, which they show in the experiments later, like which combination has the best performance. So okay. So okay, now we need to generate synthetic data. We use service LLMs to do that. They mention here, employ the trained subsets as seeds. I'm not sure what does seeds in here meaning. That maybe they explain it in the appendix, but I didn't have time. So I'm not sure, but my hunch is that, like, basically maybe it's like an example that the LLMs can be used to generate similar synthetic data, but I'm not sure. So if
That
anyone,
makes sense to me.
yeah,
But probably maybe that would be like a reviewer comment, that because usually seeds, I think the confusion is like usually a seed is like a random seed.
yeah, exactly. That's what I thought. I was
And
like,
here it's a metaphor.
yeah, yeah, exactly. That's why I was like, this is not a random set that I know. Anyway. Okay, so we generate the synthetic data. We want to make sure that we don't have duplicated data. So they filter out duplicated data as well as the low quality examples, which I guess this is also human, but I'm not sure. Like maybe they put more explanation in the appendix. Okay, and also the next bit is to make sure that the generated synthetic data is not really similar to the test data. Otherwise, then it will be like overfitting, and the model will be very easy to run this job. Okay, so that's the data generation, and it will be done iteratively until we reach the performance we want. So now, okay, let's talk about the experiments. Yeah, just to recap, there are summarization, classification, coding, close question and answering tasks in these experiments, and they also want to check what is the impact of the dataset size, so related to Arvid's question earlier, and the different combination of the service LLMs used as the data generation as well as the evaluator. And lastly, they also made some calculation on how much cost we can save by doing this method. So for the dataset itself, they use what they call this no robots dataset. I've never heard about this dataset before. Yeah, it says it has this 10,000 high quality prompt and responses across 10 categories. This is the actual dataset to start with, and later we will add with the synthetic data. And they use, yeah, just to recap again, they use this GPT-4o, Claude 3 Sonnet, Gemini as, yeah, I heard something. Oh, okay. Well, thanks, Anna. And yeah, for the smaller LLMs, we use this Gemma to be 2 bytes and 7 bytes. I guess it's bytes. It's Mistral and
Billion.
sorry, okay, billions.
Like
Sorry, I
billion
missed it in
parameters.
Llama 3. Okay. But to keep in mind that this paper is not trying to sell the idea of like using this particular LLMs, but more about the methods. So this is model agnostic. Yeah, I will say that the experiments here is quite detailed, but the high level takeaway is that this method works with different kind of models, but not necessarily like tied to a particular model. So this is model agnostic. Oh yeah, this is the thing that I was looking for before. So okay, for the synthetic data set, there are 300,000 samples. But I'm not sure whether this, oh yeah, 300,000 samples in total. And later they show that they try to fine tune with like smaller amount and then going up, and see how the performance change over the number of samples. They use LSH, locality sensitivity hashing, to remove the duplication in the data set, and they use Rouge to get meaningful variations, which like I'm not really clear on how they can use Rouge. This is not the point of this paper, which is like, because I thought Rouge is that like looking at the n-grams and how to know how they can use it as like standalone, like a single method to check the variations of the data set. But yeah, this is not the main point of this paper. Yeah.
One thing I would say is I think it's an interesting thing to point out, because usually you hear the opposite, that these like more old school metrics aren't very good at assessing data quality. So here it works, and I'm wondering if it's because of the data set they chose, or because like why do these old school metrics that don't really look at the semantics of the example work?
Yeah, good point. They might explain it on the appendix though, if anyone is curious. But yeah, I think this is really good point. Yeah, so yeah, they vary the number of data set. They use QLoRa and PEFT for the fine tuning. And as we talked before, they generate multiple responses, and this experiment they use 4. And they use 3 different service LLMs as evaluator. The metrics are the similarity between the generated and the ground truth responses, and the precision like between the input prompt and the generated response. And remember, we also talked about the threshold that we expect like to be good, like what is the minimum like the value of the matrix before we can say that it's good. They use this number of like between 50 and 70. Okay, so yeah, this is the table when they show how different tasks perform with different service LLMs as the baseline performance with like different service LLMs as an evaluator. And what I highlight here is based on what I highlight on the text. So we can quickly look into here. Like for example, we can look at the summarization task here, where Llama 3 8 billion is the fine-tuned smaller LLMs. Oh yeah, the number on the like before the slash is the, my understanding is that it's the mean over all the responses, you know, the number of responses also times the number of evaluation, while the second number here is the number when we only pick the examples that are above the threshold as a metric. That's my understanding, but I'm not 100% sure on it. Okay, so basically for this Llama 3 8 billion, we can see that the mean score, just look at the left one, is around 87%, while the benchmark, the service LLM benchmark, is around like 92 and between 92 91.9.95 to be precise, to 94. So it's still slightly worse, but it's like quite close for the summarization. And for this, and they also highlight that like different smaller LLMs have different performance. So it really depends. Like, okay, now if you want to do summarization, yes, this Llama 3 is the best. But let's say you want to do a closed question answering task that, okay, now like Gemma 7 billion is a better. So like one of the key takeaways that I want to show with this experiments is that you need to know like which I would say like you cannot generalize like this model is the best model for all tasks. Like certain models are better at certain tasks, and different ones are better at different tasks. But this method is a model agnostic method, so that even though you need different models for different tasks, yes, you can achieve a really good performance. So to me, that's the takeaway that I want to emphasize in this experiments. Yeah, we can also like see here like for different tasks like coding, Gemma 7 billion is really good. Yeah, roughly I would say like Gemma 7 is really good in general, and also Llama. But okay, let's just go through here, because they also show here that, oh, they have a small note here that even though Gemma 2 billion seems to be not as good as the 7 billion version, but there are like some conditions that Gemma 2 billions is like comparable with the later one. Yes, Peter?
One thing I was wondering is, in the results, is there anywhere where they like, I think the strong assumption for the paper, not a bad assumption, but a strong one, is that the LLM that you're using to generate the data, so like a proprietary LLM, is good enough at the task that you can use it to generate useful synthetic data. And so I would actually be interested to see if they could, like, if they have an experiment where they choose somehow to make the model worse and worse as a starting point for the service like the task that the service model is being used for, and then seeing if at some point these methods of fine tuning the smaller open source ones stop working.
Yeah, well, I'm curious. I think I mentioned a bit earlier. I'm not sure how they mentioned that for the original data, there are humans who curate the data to make sure that we use the high quality examples. But for the synthetic data, how do they measure? How do they make sure that we only use the high quality data for the synthetic? That's, yeah, I don't know whether like they have separate process, or it's also human, or they didn't even check at all. Yeah, but I do agree that they have this assumption. Yeah, cool. That's a good point. Okay, so yeah. I remember Arvid asked a question earlier about the number of data points they use. They also did experiments here to compare like how many data points you need actually before you can get a comparable performance, and like what is the minimum for that, because at some point maybe there is no point of increasing your data points because it will saturate, which they show here. So yeah, after 4K, so the first column is for GPT-4o as the synthetic data generator. The second column is Cloud Sonnet, and then the third column is Gemini 1.5. So the point that they want to highlight here is that after 64K, after that you achieved saturation, meaning that even though we added more data in our evaluation, it doesn't improve much because it's already really good at 64. So
one question, but that is against the response of the big model, right?
yeah,
That doesn't necessarily mean, say, if I were to create my own data set that is perhaps a lot smaller than that, but fine tune on that, I might get something that is better on that particular task. No,
you mean that because it assumed that the service LLM is the benchmark, but basically you can still outperform the service LLM.
yes,
Yeah,
and of course it becomes a question is how much can you outperform, or how much data do you have to have in order to outperform it? But
yeah,
we know synthetic data has its issues because it's not real data, so it can it can amplify biases and all of those sort of things.
yeah, that's true. I think because the point they want to sell in this paper is that we have these service LLMs that not people usually use, and then how we can achieve similar performance with this data, but it doesn't handle the case where okay, we want to outperform it. And
because I always thought that was like one of the big arguments for having your own LLM in house, like Bloomberg or so, that is it's simply not good enough using generic LLM for very, very specific tasks.
yeah, correct. Last bit, not almost like second to last bit. No, I think that's the last bit. I'm not going to emphasize much more in this. Here basically they want to show how the precision versus similarity compared between these three different service LLMs as evaluators. And for example, you can see here for Gemini 1.5 that it has lower similarity. So that's why you see like the curve is a bit banded down, because the y-axis is the similarity and the x-axis is precision. So meaning that this, when it's like bended down, it's like it has lower similarity compared to the other models, but precision looks good. So they also want to say here that well, it really depends what you're looking for. Also in terms of metrics, that's how you can choose your model. But again, this is model agnostic, so you can use whatever you want based on your use case. So that's my takeaway on this. Yeah, okay. Last bit is the cost, which is like a very huge a benefit on this. So they mentioned that, okay, first we need to think, what is the cost incurred for calling service LLMs? For service LLMs, you need to like every time you call, it will depend on the number of tokens. And yeah, and basically the cost will increase through time because you will keep calling the models. But for the small function LLMs, the cost will be higher in the beginning because first, definitely you need to fine tune. And in their case, they use like 8 A100 GPUs, and then the fine tune cost less than $800. And then after that, they need to deploy this small fine tune LLMs, and they use L4 GPU. Yeah, so there is like a cost of fine tuning and deployment in the beginning. But then after that, basically the cost will come from the electricity, which they claim here the power consumption for each server is only around $30 per month. So that means that we see here in this curve that, okay, at first you see the flat lines here is basically the fine-tuned smaller LLMs. At first, it's higher than the service LLMs because of that fine-tuning and setting up the deployment cost in the beginning. But after that, it's basically flat because you just need to pay for the electricity. But for the big service LLMs, then the cost will always increase over time because you need to keep calling the LLMs. And they say that you will start save money after 2 months. You know, when when the cost of using service LLM starts to go higher than the fine-tune smaller LLMs. Yeah, that's it about this paper. My thoughts on it also, yeah, well, besides this cost, my first thought is like, okay, this is an ideal cost that you don't need more cost to maintain the model. I'm not sure whether, in reality you will need like more you need to have the maybe capability, like the technical skills of the people also to maintain this deployment, because if you're a very small team, and basically calling service LLMs is much easier in terms of like managing your own LLMs. So maybe that's another cost that's not calculated here. And my second thoughts was like, for this paper in general, does it mean that they are saying that as long as you have good quality data set with enough amount, you can basically surpass the big LLM's performance? Does it mean that basically you don't need more parameters to achieve similar performance, and you can basically like you can compensate the number of parameters by having more data? So that's the question I'm thinking. And yeah, any more thoughts or comments? Please feel free. I think this is the end of the paper.
I don't know if I think if you don't do anything extra and you just generate data from the LLM, then I don't see how you can get better performance in the LLM.
Sorry, say it again.
If you don't do anything except generate model, or like not to generate data using the service LLM, I don't know how you get the smaller models to perform better. Maybe I'm
Yeah. So what do you imply? Do you mean that you still need like a service alarm to generate high quality data, and it's not easily, you cannot easily. Mhm.
What I'm saying is that I think if you want to use the service LLM to generate data and get better performance in the service LLM, then you do need like a human in the loop to curate the data set to choose like the good examples versus the bad examples.
Yeah, which I agree. But still, like, do you think that if we have really good examples with enough amount of data, we can achieve much better performance, like without even having larger model, no matter how we can generate the data?
It's a tough one. You should if you have better data than what the model was trained on.
Yes, Julian.
This is a practical, and thank you very much for that. Hopefully this might be useful to somebody, is that we've wrestled with this matter of local LLMs versus cloud LLMs for about a year. And I spent a long time and apparently too much money, and we've ended up with what I call 3 LLM servers, 2 each running a 3060, and the really hard one was running a twin 3090. This may be nothing for NPlan, but for a small shop, it was a hell of a job getting it working. And I did think until recently I'd probably wasted my time and money on this. Probably cost £3,000 or something. But actually recently I've started to think that I'm really pleased I've done it. And one of the reasons is it's orthogonal to this paper, but with the quantization that's going on now, I'm able to run, for instance, Reflection 70B. When that came out, some kind person put it on a llama within days. So I was able to try it. There was a furore and was it a scam and so forth. And I personally think it's not, because it works quite nicely. But I can run virtually any 70B model on this setup now. So just from a practical point of view, since it's in this area of the paper, I would actually encourage people to try and go it on their own, but always be aware of the fact, and we're highly aware of the fact that we will have to switch to the cloud. But I just hate the idea of just racking up all those charges, especially for a test that goes wrong. I mean, all our tests are literally just the electricity. So I can think, well, it doesn't really matter. If it takes that long, yeah, I have to pay for the electricity. But I don't really care if it goes wrong. So I'll take the risk. And that to me is really important. And also having 3 of these things going on, we can offload bits and pieces. It means and you talked about having a human in the loop to manage this. I mean, for me, the big problem was actually just loading CUDA, getting CUDA to install. And if anybody ever wants to know about the practicalities of doing that, I'll share. I won't say now. But it is a big pain, in my opinion. And you also have to watch that your VRAM doesn't overflow. That's very tricky to do. So anyway, those are just some sort of comments from the field, but I definitely think it's worth doing.
Cool. So just to make sure I understand, so what do you think are the key benefits, like besides money? Like, yeah, you don't need to go.
As I say, you can try increasingly large models because of the quantization, and you can try experiments. You can try running a fine tuning. You can try anything. This is not going to cost you $1,000. You don't have to answer to your pocketbook or your boss or anybody else, because it's such a small amount of money. So that's the main thing. And I'm hugely in favor of experimentation and trying things. And I always remember this thing. Just imagine if everybody had to pay for each word they said. Right. This is a genuine thought experiment. What if you had to pay a cent for every word you said? You'd be constantly second guessing. Well, is this word going to work? Is this sentence going to work? What will I get? It would be a disaster for communication. So again, the same thing for experimentation in LLMs. You want to have a very, very small cost, I think, anyway, for trying things. So you can think, well, this is probably a stupid idea, but why don't I try it? Just because. And sometimes crazy ideas really yield something quite unexpected. So that would be my take.
Cool. Thank you, Julian, for sharing. Yeah. Anything else? Cool. So I will stop sharing then.
Great. Thank you, Inneke. That was a cool paper. It was interesting to see like something a little bit more on the engineering side of ML. But everyone have a good day and a good weekend, and hopefully we'll see you here next week.
Thank you.
Very much.
Bye.
Goodbye.
Amazing. Thank you.